All right, so this is kind of a different video. Like I mentioned at the end of the last one, this lesson, which refers to section 8.3 in the textbook, doesn't require any new concepts, so there's no notes for this. All the sort of ideas have already been covered in previous notes. It's really just about looking at a variety of problems that at some point can use linear systems. It's not an easy lesson, so please don't think because there's no notes it's somehow meant to be easy. But it doesn't require, again, new concepts. So what I'm going to do here is work through 3 of the homework problems. I'm going to work through question 3, I'm going to work through question 6, and I'm going to work through question 9. So I will say I highly recommend against watching any of these videos until you've tried these first. Like I said, you can try this homework. Once you've seen the previous videos, you can just start trying it because there's no, again, new concepts you need. But once you've tried these questions, then I'm going to show you how I would approach it. Keep in mind, there's always more than one way for any question. All right, so question 3. It says, in January, the average high temperature for White Rock is 11.8 degrees greater than 100 Mile House's average high temperature. So on average, you can see White Rock in January is 11.8 degrees warmer than 100 Mile House. The sum of these two temperatures is minus 2 or negative 2.6 degrees Celsius. What is the average high temperature in January for each of these two places? All right, so first, what are the two unknowns? Well, the two unknowns, in this case, they make it pretty clear, the average high temperature for each of the two places. So White Rock and 100 Mile House. So over here, I'll pick a variable, also put W for not just White Rock, but for the average high temperature in White Rock in January, but I'll just write that. And for 100 Mile House, I'll put an H. And that's the average high temperature in 100 Mile House. Okay, so W and H. I could use X and Y, but then I think it's a better chance of me mixing up what these things stand for. All right, so next I need to make a system. And I look at my information. What's one thing I know? If I look at the first sentence, it says the average high temperature in White Rock is 11.8 degrees greater or more than 100 Mile House's average high temperature. So I can express that by saying the temperature in White Rock, W, it equals the average temperature in 100 Mile House plus 11.8. Because if you notice what it says here is that White Rock is 11.8 degrees more. That's what you see here. White Rock is 11.8 more than 100 Mile House. There's other ways of writing it, but I think I think this is a fairly quick way. And so again, W is White Rock, H is 100 Mile House. All right, I need a second equation. The second equation comes from this sentence right here. The sum of these two temperatures is 2.6 degrees Celsius. So sum means what you get when you add the two values. So I know if I add these two values, I get negative 2.6. So I know if I go W plus H, I get negative 2.6. And now I've got the hardest part of the question done, which was creating my system, and now I can solve the system. I can use elimination, I can use substitution. I'm going to use substitution because in my very first equation, it already is solved for W, right? W equals all of this, so I don't have to rearrange anything. I can take this and substitute it right there, right off the bat. I don't have to rearrange anything. I don't have to use elimination by multiplying anything. It's kind of set up quite nicely for that. So I can take a look at the second equation now and rewrite it as, instead of W plus H equals negative 2.6, I write as H plus 11.8. Again, all that was where my W was. Right? I substituted W for H plus 11.8, and then write the rest of the equation. Plus H equals negative 2.6. And now I have one equation with one variable. Yes, it repeats twice, but I can combine like terms to put this together. So let's combine like terms. I get 2 times H plus 11.8 equals negative 2.6. I want to solve for H, so I want to subtract 11.8 from both sides. So I have 2H. Negative 2.6, take away 11.8 is even more negative. It's negative 14.4. And finally divide both sides by 2. And I'm not done my work, but I have one of my answers, and I'm almost done my work. So H equals negative 7.2. So what does that mean? That means the average temperature, the average high temperature in 100 Mile House in January is negative 7.2 degrees Celsius. there's one of my two answers. But I also need to figure out for white rock. And so with that said, I can put that negative 7.2 for h into any equation I see up here that has a, I might as well put it into the very first one, because this equation right here, the very first one, is set up to tell me the average temperature in white rock. All I got to do is take the answer I just found and add 11.8. So let's do that. So white rock's temperature will be the same as the temperature I just found plus 11.8. Now when I'm working with equations, I don't put units into them. But negative 7.2 plus 11.8 is 4.6 degrees Celsius for white rock. And now I'm done. Notice every time we use substitution, we end up with, it takes most of our work to find the first solution, in this case 100-mile houses temperature, and then it should be very, very quick to find the other. In this case, white rock's temperature. All right, so next I'll look at question 6. And like I said, if you haven't tried these questions yet, please don't watch the video yet. You want to try these first. But I'm looking at two types of bulbs, an incandescent bulb, which is kind of the old school bulb that has a filament that glows in the middle, like a piece of metal almost that glows, and an LED bulb, which you see more and more often these days. And it says, in this case, the incandescent bulb is cheaper, but costs more per hour to operate. And the LED bulb is more expensive, but costs less per hour to operate. Now, I will say in this question, and again, I'm assuming you've tried the question, they give us some information that's not necessary. The 60 watts, the 10 watts, those don't really matter. So, they're not wrong, but I don't need to take those into account. And so what are the unknowns I'm looking at here? Well, it's cost and time. And so I even get the idea of time right here. It says how many hours will it take for the LED bulb to be less expensive. So we're comparing time and cost together. And so let me create equations for cost and time. And so first let me look at the LED bulb. Actually, I'll look at the incandescent first. I'll try to spell this right. All right, the incandescent bulb. The cost of it, it tells you, is $3.25, but you're going to use it, I presume. So plus $0.0072 per hour. So I'll say times T for time. And I'm going to know that T stands for the time in hours, and C is the cost of operating it after so much time, right? Because while the bulb costs $3.25, assuming you turn it on at some point, it'll eventually cost you more money than that. So then I have the same idea for LED. The cost of this is more initially, but it's less per hour. It's 0.0012 T. And again, in this case, cost is the overall cost of this bulb, and T is the time in hours that I'm using it. All right, so again, I think I've got the hardest part of the question done, but now I want to solve this. And how do I solve this? I could use elimination, but like before, I have, in fact, both my equations already solved for C. So all of this I'm underlining in red equals C, which means all of this I'm underlining in red I can put right there, or vice versa. And so if I do that, I get 3.25 plus 0.0072T equals this side, 6.25 plus 0.0012T. At this point, the most annoying thing about this question is the decimals, but again, I would encourage you to use a calculator. And now notice I have one equation with just one variable. Yeah, it's on either side of the equation, but it's only one variable, just a variable t, so I know I can solve this. I'm going to try doing two steps at once here. I'm going to subtract one of my t terms. I always like to subtract the smaller one, so I'm going to subtract 0.0012t from both sides. But while I'm at it, to save myself time, I can see that that term's going to cancel out. So I'm going to also subtract 3.25 from both sides. So I can see that cancels out. And then I can just see that I'll have a t variable on one side and a constant on the other. Again, if you don't want to do this in one step, then do it in two steps. But on the left-hand side, I have 0.0072t, take away 0.0012t. Feel free to use a calculator. You get 0.006t. On the right-hand side, I have $6.25 minus $3.25. That's exactly 3. And so finally, to figure out what t is, I just need to divide both sides by the coefficient right here, 0.006. And whatever 3 divided by 0.006 is will be my answer for t, which comes to 500. So now, what does that mean? Well, 500 was t. T is hours of use. So this tells me, after 500 hours of use, at that instant, the two bulbs cost the same. But the question was asking, how many hours will it take for the LED bulb to be less expensive? Well, keep in mind, right from the start, I can see the LED bulb costs more. So I know if I just buy these two bulbs and I don't use them, yeah, the incandescent bulb is cheaper. But over time, eventually, the LED bulb must become the better deal because it's cheaper to operate if we use it enough. And that's what we've discovered here. 500 hours this is the number of hours. So 500 hours for the LED bulb to become a better deal, or be less expensive overall. So the last question asks, is it worth using an LED bulb? Well, it depends how often you're going to use the bulb. Very clearly, if you use a bulb more than 500 hours in total, yeah, the LED is a better deal. And honestly, 500 hours is not a lot. You know, if you had a bulb on for half a day, 500 divided by 12 for half a day, for 12 hours, is about 42, which means after about 42 days, the LED would be cheaper. But really, it depends on how much you're using it. So that last part depends us to think about, is 500 hours a lot? Is that a reasonable amount to make it cheaper? Honestly, 500 hours is not a lot for a light bulb. But keep in mind, you have to kind of think about the context of the question for that point. All right, the last question I'm going to work through is question 9. There's that bell. And so for this, I have a table. And they're looking at year after year how the population of fish in a lake compares to the population of fish being eaten by osprey, a type of bird. And hopefully the pattern's fairly clear. For fish, every year, it's going down by 1,000. And for the fish that are eaten by the osprey, it's going up by 200. So every year, 200 more fish are being eaten by osprey, and every year there's 1,000 less fish in the lake. Okay, so I've pretty much answered question A. So the main part is write a system to represent the populations of fish. Now, what I really think they should make clear is they're talking about the two populations, the populations of fish in the lake and the populations of fish being eaten. I really wish they'd make that more clear. Really, I want to turn these two linear patterns into a pair of equations. There's a few ways I can do it. This would be a little bit easier if they start at year 0. Now, year 0 just means the start. They start at year 1, which is, they're saying that's the first year. But I just got to be a little bit careful because if I say my equation for fish in the lake, if I say it's something like this, the number of fish in the lake equals 10,000 minus 1,000 times every year, this is wrong because this implies at time 0 there was 10,000 fish, but it was year 1, not year 0. And so we have a few ways around this. One thing is to treat this as an arithmetic sequence. This is actually quite nice to work with as an arithmetic sequence because sequences start with term 1. And so I'm actually going to treat this as an arithmetic sequence, which you hopefully recall is a type of linear function. And I'll do it for both. And so I'm going to treat that year as being like the term number. And so for fish in the lake, I'll kind of write this one in red. Don't forget that any arithmetic sequence can be summarized like this. The general term is the same as the first term plus the common difference times n minus 1. And so in this case, instead of Tn, I'm going to put f for the number of fish in the lake. T1 is 10,000. The common difference is minus 1,000, so actually I'll change that plus to a minus. Times n minus 1, I'll put t minus 1 I want t to stand for the year, time. And then if I clean this up, distribute the 1,000, I get 10,000 minus 1,000 t plus 1,000, right? A negative times a negative is a positive. And combined like terms, I get 11,000 minus 1,000 t. So that's my equation to represent the number of fish in the lake as a function of the year number. Year 1, year 2, year 3, year 4, and so on. So I can do the same thing for Osprey now. Again, using that same form of the general term for any arithmetic sequence. In this case, I'm going to use fish again, F for the number of fish. This time it's fish being eaten, though. My first term is 700. The common difference is going up by 200 each time. So you clean this up. I'll just save a bit of time. You get 500 plus 200t. So I just skipped a step. I just skipped the step where I expanded that and then combined in like terms. All right, so there's my two equations for the populations of osprey. This is the population of osprey in the lake. This is the population of osprey being eaten each year in the lake by the osprey. This is the population of fish in the lake. This is the population of fish being eaten by osprey. Okay, then it says to solve this system. It actually says to solve it graphically, so I'll do that graphically. And then what does the solution represent? Okay, so that's it. This would be a pretty easy system to solve algebraically as well. I could treat it like the last question and just substitute all of this right there. But I'll solve it graphically, so I'm going to switch to Desmos, in which I just type these two equations in. I have y for f and x for t. And I see this. Okay, it's because I have to adjust my zoom settings. Now, if I just zoom out, that's a terrible graph. And why? Because I'm looking. Think of my x-axis. This 400 right here, that's 400. That's year 400, and this is negative 400. Is 400 years in the past. So I definitely want to compress my scales. I want to compress my y scale way down and stretch my x scale way out. There we go. Now I'm seeing, 10 years into the future and so on. Now the graph in red must be the population of fish because it's going down. The graph in blue must be the population of fish being consumed by osprey. It's going up. My solution is right there. And so what does that solution represent? Well, that means according to this pattern we're seeing, if it continues, and that's a key word, if this pattern continues of how the population of fish and the population of fish being eaten by the osprey continues, then in year 8.75, so almost year 9, or sometime in the 8th year, the population of fish will be the same as the population of fish being eaten by osprey. Which, if that actually happens, well then right after that there'll be no more fish left because every single fish has been consumed by the osprey in that 1 year. But that's what that means. So realistically, what that means is that fairly soon this pattern has to break down. It definitely can't continue. I mean, according to this, in year 10, in year 10, according to this model, there will be only 1,000 fish in the lake, and that same year there'll be 1,000 fish in the lake, but there will be almost 2,500 fish eaten by osprey. That doesn't make sense. There's only 1,000 fish in the lake. And so definitely at that point there, that system kind of shows when the two populations of fish and the populations being fish consumed are the same. So really, realistically, before then, something's going to change. All right, but that's what it represents, right? And so with that said, those three problems are all a little bit different. And I said, hopefully you tried each of these problems before I showed you the videos. By the way, that finishes videos for this entire big unit.